Welcome to a lesson with Dr. Powell. Let's take a look at an example of a line integral. So we need a vector field. And let's suppose this one is something like x plus y, and maybe just simply y. Okay, now let's also give ourselves a curve. Let's give this curve, say suppose this curve is from a parameterization in terms of t. Maybe it's something just rather simple. Maybe it's something like t comma 1 plus t squared or something like that. Okay, so we have our curve, we have this, and that's all we need to describe an integral. There's different notations for this. We could use the notation f dr, where we've described where we know what c is, we've labeled it, we know what f is, and this is enough. Or we could rewrite this as x plus y as a differential one form here, plus y dy. Now that would be fine too if we write a c here. This means that we're integrating this particular vector field. This is kind of nice because this kind of, in this notation, we actually see what the vector is. We could have written the vector there as well, but it's okay either way. For theorems that we're going to be doing later in different vector computations we're going to be making, sometimes a differential one form notation is actually advantageous, and we'll see that later. But nonetheless, it means the same thing. Okay, so let's go ahead and actually work through this computation. All right, so we simply replace x and y with what they are here on the particular curve. So this would be a t plus 1 plus t squared. And dx, you replace it with what it is. What is dx? Dx literally is, well, x is t, so dx is equal to dt. So it's just dt. And you could write it like that. You could write it like this. Now c, let's see, we actually need an interval for t to be on. Let's just make it simple. Let's go from 0 to 1. So c is not complete without knowing where your parameter is going to be living. Suppose it's going from 0 to 1. Now, true, we could put a dt here. We don't have to. We could, factor it out at the end, but this is fine too. We can do it this way. Here on the y, we get 1 plus t squared. And what is dy? So we have to actually work out what dy is. So dy is equal to the derivative of y, so which is 2t, and then times dt. So we end up getting that times 2t dt. All right. Now, like we said before, if we just did the dot product here with dr, and if we thought of this as dx dy, dt here, we could just kind of keep the dt factored out of everything. We could have, and we would have seen the exact same thing in this computation. We just did it kind of piecemeal here. In fact, we could extend this integral to just cover everything if we wanted to at this point. Maybe we'll do that. So we have t plus 1 plus t squared, and we have this right here. So let's just make this one big integral. 0, 1. Let's see, we got t plus 1 plus t squared plus, and we can multiply that through, plus 2t and then 2t cubed. Okay, and then maybe combine like terms. We see, okay, so that's going to be the integral from 0 to 1 of 2t cubed plus t squared plus 3t plus 1 dt. Okay, now we integrate. So we end up getting, let's see, 1/2 t to the 4th plus t cubed over 3 plus 3/2 t plus t, and we go from 0 to 1. So we plug in 0, we'll just have 0 everywhere. So we plug in 1, and we end up getting 1/2 plus 1/3 plus 3/2 plus 1, which ends up being 2, 3, 3 and yeah, 3 1/3, which is same thing as saying 10/3. So we've been successful at doing a little integration. Now, again, we'll talk about what this means at another video, but for now, we're just this is an example of how we can take a vector field and then we can integrate it over a curve. And we did it, and we ended up getting a specific number or value, just like you would if you took a function and you integrated it along a straight line. Even integration along an x-axis with x coordinates, it could be considered a line integral in some sense, but you only have one component in one direction. And so it's kind of a simple one. If you wanted to beef it up to two components, I suppose that would be also possible in that case. But for instance, maybe if your vector field itself only had something in the x direction, what if you just had an f of x and it didn't depend on y? And even if you just had, and then if you had a 0 here, and this was your vector f, and then you're dotting it with dx, dy, notice what happens. You have a 0 coming from there, and you're just left with f of x dx. And especially if your parameterization is just x equals t, we have a nice line integral. So really, anytime you integrate with a single variable, you actually have been doing a line integral without realizing it. This is just an example of generalization to that idea. When our axis, where we're taking coordinates on, is curvy and not necessarily straight. Thanks for watching.